Hello, and welcome to the next session in my C STL by example webinar series. Today, we're going to be focusing on one of the key unordered associative containers, the set, and its sibling, the multiset. As you may recall, a set simply allows unique keys, whereas a multiset allows duplicate keys. So without any further ado, let's go ahead and take a look at the source code we'll be covering, and then we'll jump right into it. I'll start by sharing my screen. And you can see here, if you go to my GitHub repository in the C STL S-05 folder, you'll find the code we're covering here in the 5.3 portion, as well as in the 5.4 portion. So let's go ahead now and take a look at the actual code to start things out with. So again, we've talked about this before, but just a quick recap. A set is a collection of ordered data that's stored in a balanced binary tree. They use a red-black tree under the hood. Not that it really matters, but it's a balanced binary tree, and that means operations like insert and find and remove all take at most log n time, where n is the number of elements in the tree. You can see the actual template here. For the set, we have the type name for the key, so it's a parameterized type. We have a type name for a compare functor, which defaults to the less functor, where it's less parameterized by key. You can change that, as we'll see when we look at the examples. And of course, it's also going to be parameterized by the allocator, which defaults to the standard allocator. That's where the memory comes from. The key characteristics of the set are that it orders the elements that are added to it. They're ordered by the comparison operation, in this case, by default, less. And as we said before, a set can only contain one copy of any element, in other words, the key that's added to it. The elements are generated by set iterators in sequence. So if you walk through the iterator, you'll get them in whatever order you've defined with the compare operation, be it ascending order using less or descending order using greater. And you'll see that the way it works under the hood is it uses whatever operator less than is defined on the type that's parameterized. If you parameterize it with a built-in type like int or double or long and so on, then it just uses the obvious operation less than that's built in. If you use a user-defined type, then it assumes that there's a less than operator defined. And so you'll need to define that if you have a user-defined type that doesn't have that already. And we'll talk more about that as we get further along into this. So let's go ahead and take a look at an example here. We're going to start out by defining a set of numbers, which will be integers. And I've just given some numbers, 2, 1, 3, 0, 7, in any old order, doesn't matter. And I gave it the greater functor, and that means it's going to be used to sort it in descending order. And of course, it'll be stored in the set in descending order. The next thing we do is we go ahead and we use the find method that's defined on the set to find the value 9. And of course, we don't see 9 in the set, so that's going to return the end iterator, indicating that we didn't get a match. So when this prints out, you'll see it says 9 not found. The next thing we do is we go ahead and we insert 9. So now that we tried to find it, didn't find it, let's go ahead and put it in there. And now when we go ahead and say how many elements are in the set, we should have 6 elements in the set because we had 5 to start with, and we just added a new one. Then just for kicks, we're going to go ahead and use the C++ generic find algorithm. And generic find is defined over here. This is part of the algorithms header, and you can see it's very, very simple. It just does a linear search from beginning to end, looking to see if there's a match. And if there is, it returns that matching iterator. Otherwise, it returns the end iterator. Obviously, this is a linear search, so you probably don't want to do that most of the time. You actually want to use the find method that's built into set, which does it in log n time. And in fact, you can see the IDE is trying to encourage us to switch over to use the find method that's defined on the set. It actually does that transformation for us. I just wanted to show it this way for kicks, but notice how the compiler is trying to nudge you to do the right thing. Then we go ahead and see whether we found it or not. Of course, this time we should find it because it's there. And then the last thing we're going to do is we're going to go ahead and print the contents of the set out. And since it's ordered in descending order, when we iterate from beginning to end, it'll print them out in beginning to end order. So let's go ahead and run the code and see what the output looks like. And lo and behold, as I said, it didn't find 9 the first time. There are 6 elements in the set. The next time we looked it up, we found it, and then we go ahead and print the contents, and it's in fact in descending order. So that's a very simple example of set. We'll look at some other examples that are a little bit more interesting, perhaps, depends on your point of view. And so speaking of which, let's go ahead and open up the next version, next sample. This implementation is going to illustrate how the set insert method works. And it has some interesting semantics to it. So here we're going to define ourselves as another set of int, except this time it's going to be ordered in ascending order because implicitly we use the less operation. So I should probably say, implicitly use less int to order this. So it'll be ordered in ascending order, not descending order. If we use greater, it'll be descending order. We then go ahead from I equals 1 to I less than or equal to 5, and we go ahead and multiply I by 10, and we put each element into the set. So we'll end up with 10, 20, 30, 40, 50. We could have done this without a loop, of course, but just for kicks, I used the loop. The next thing that we do is we go ahead and we try to reinsert 20. Now remember, a set can only have one element. It can only have one key. And so if we try to insert it again, then we're going to get back something that indicates it didn't work. And what comes back here is actually a pair, although as you can see in this case, I'm using an auto, but in fact, under the hood, it's actually using a pair. And it's going to be a pair of an iterator for the set and a bool. So what does that mean? Well, what you'll see is that the second value that comes back is going to indicate whether or not we inserted it or not, whether it was successful. So if it's successful in inserting, the second value that comes back from insert will be true because it says it inserted. But in this case, it didn't insert because it was already there. So in that case, it's actually false. So if it's false, which it should be, we come over here and now we take the first field in that pair, which is going to be the element that we were trying to insert. It's pointing to 20. And again, just for kicks, we use auto here. We could have written this out in a more verbose way. We could have said set int iterator, if I could spell, and if I could put the syntax in correctly and so on. But that's probably not the best thing to do because that's kind of verbose. So let's just go ahead and keep it with good old auto and just say auto is so that you know what it is under the hood. So at this point, we now are pointing to the element 20. What we're going to do now is we're going to go ahead and insert 25 and 24. And we're going to use the iterator as a hint or a heuristic. And it turns out if the iterator is positioned in just such a way where you can insert, or where the insert algorithm can quickly determine where the element goes without having to search from the top of the tree, then it'll be optimized, as it would be in this case for 24 and 25. When we do to 26, however, let's say for sake of argument that the underlying implementation would not be able to determine very quickly that that was in fact the right place to put the item. So in that case, it would go ahead and start at the top of the tree and then find the location in the tree where it has to go. So giving an insert call with an iterator is a way to give it a hint that may lead to optimization and may not, but in any case, it won't change the asymptotic time complexity. It'll still be log n. Then for kicks, let's go ahead and show how you can use insert to add a range of elements in one fell swoop. So here we're going to add the range 5, 10, and 15. I guess range isn't quite the right word, but we're going to put 3 elements into the set in one fell swoop. Or we're going to try to put 3 elements into the set in one fell swoop. In this case, of course, 10 is already in the set, so we'll only end up inserting 5 and 15. And that 10 will simply fail silently. And then the last thing we do is we go ahead and print the contents out. So let's go ahead and run the code, see what we get. So as you can see, what we ended up with, we started out with 10, 20, 30, 40, 50. Then we added 24 and 25 and 26. So you can see that those are in there. And then we added 5 and 15. So the final result was 5, 10, 15, 20, 24, 25, 26, 30, 40, 50, which is in fact correct given what we have done here. So that's illustrating some other interesting aspects of set, in particular looking at ways you can do insert and seeing what happens when you try to insert duplicates, see what happens when you can give hints to do inserts, and seeing what happens when you want to insert a group of elements in an initializer list in one fell swoop. And there's other ways to do that as well. You could use iterators and other types of techniques to insert groups of elements in one fell swoop. Okay, let's go ahead now and turn our attention to the next example. And this example is going to create a bunch of sets and then use the swap algorithm. We talked about swap in a previous video when we were talking about exception safety. And you may recall I talked about the fact that swap is very useful when you're trying to write strongly exception-safe assignment operators, for example. It has other purposes as well, and we're going to demonstrate a simple example here. So we start out by making ourselves a first set, which just has a bunch of values. They appear in no particular order, but of course the set will store them in ascending order using the balanced red-black tree under the hood. We then go ahead and assign first set to a const reference to a set. So this will not make a deep copy. This just basically means we now have another reference pointing to first set in a sort of a Java-esque like way. Then what we do is we take the second set, which is actually just referring to the first set, its contents, and we copy the elements from second set into a C STL list, which we give the very unimaginative name a list. So you can see here we now have a list that has the same contents as both the first and the second set for that matter. Then we go ahead and we make a third set, except this third set is going to be arranged in descending order because we use the greater functor here instead of using the less functor. And once again, you'll notice how we start with the beginning of a list and go to the end of a list. So this is illustrating how you can use iterator ranges to copy arbitrary containers to other arbitrary containers. And you don't actually have constructors. There's no constructor for lists that takes a set. There's no constructor for set that takes a list. Instead, it simply takes the iterator ranges as we're seeing here, which works out very nicely. And the last thing we do is we go ahead and we make ourselves a fourth set, and then we swap the contents, or really the references and the internal data members of the contents between the first set and the fourth set. So that doesn't actually do any data copying. It just swaps the internal data members around. So what we do now is we're going to go ahead and print out the third set and print out the fourth set, and let's see what we end up with when we run this code. And as you can see, basically what we end up with is the set's contents for the third set sorted in descending order. And that's because we gave it the list copies up here, which we're in. And then the one that's the fourth set, which is swapped with the first one, that was in ascending order. So you can see that the third set was used with the greater functor, so it's in descending order. And you can see the fourth set got the first set's contents, and those were sorted in ascending order. So that's what happens when we get the results out. So this is illustrating a whole bunch of other very interesting set features that I think are worth understanding. All right, let's go ahead and take a look at yet another one. That was D. Let's go ahead and take a look at E. And this is illustrating a couple of interesting things about sets and multisets for that matter. The iterators that are returned from begin and end on a set are special. They're different from the ones we've seen so far for the other containers like vector or dec and list, where you could actually change the contents of the underlying container as you were iterating through it. Basically, they were non-const iterators for those sequential data types, sequential containers. For cases of the ordered associative containers, such as set, multiset, map, and multimap, in that case, the iterators are const, which makes a lot of sense because you don't want to be able to change the elements as you're iterating through them, because then the organization of the red-black balanced binary tree would be chaotically modified and corrupted, and that would cause chaos and insanity, as you can imagine. There's also reverse iterators that you can use just like normal that give you the ability to go backwards through the set contents. If you want to get rid of elements in a set, there's various ways to do this. You can erase a particular element. You can also erase things using an iterator. And finally, you can erase a range. And we're going to talk about all these aspects in this example. So the first thing we do here is we make ourselves a first set, which, as you can see, is just going to be a bunch of values. And I guess to be more modern C++y, I should get rid of these extraneous parens because we don't need them anymore. So we're going to go ahead and make a set that, of course, will be ordered in ascending order, and then we go ahead and print that out. Then we're going to go ahead and erase the elements, the element 4, and you can see there was a 4 here, so we're going to get rid of 4. Then we're going to go ahead and look up the element 5, and we're going to get an iterator back to it. So this is actually an iterator to a set element, because we're going to find it. And then we can use that iterator, which again, we gave the somewhat unimaginative name 5. So we're going to erase it by its iterator. So you can see you can erase it by the value. You can also erase an element by an iterator that references it. And then we're going to go ahead and print the contents of the set. And then the last thing we're going to do here is we're going to go ahead and find ourselves the element 6 and find ourselves the element 8. And remember that the set is ordered in ascending order. So then what we're going to do is we're going to say, hey, please go ahead and erase from 6 up to but not including 8. So that's going to go ahead and get rid of 6 and 7, but not 8. And then we're going to print the results in reverse order. So here we print the results in forward order. We print the results first in forward order, print the results in forward order, and then last we print the results in reverse order. So let's go ahead and run this thing and see what we get. So as you can see, the original set contained the values basically 1, 2, 3, 4, 5, 6, 7, 8, and we print those out. Then we went ahead and removed 4 and 5 and printed that in ascending order. So 4 and 5 have disappeared, of course. And then the last thing we do is we get rid of the range 6 to 7, and then we do a print from the end to the beginning using R begin and R end. And I guess just for kicks, I probably could have done something like this. Could have made this a reverse, whoops, if I could spell. Come on. All right, let's try that again. Here we go, reverse copy. So if I make this a reverse copy, then we're going to also print it backwards, except we don't have to use R begin and R end. We can use begin and end. So let's go ahead and print that out just for kicks and see what results we get. And lo and behold, we get those backwards because we did a reverse copy. Whereas down here, we did a copy, but we started at the end with R begin and then going to R end. So this is showing you a whole bunch of different ways to manipulate sets and combine them with various kinds of iterators. And I should, again, hasten to point out that you can't make any changes to something when you have an iterator to it. So down here, for example, I couldn't have said, 5 equal 100 or something like that. And the reason why is because you can't assign to it because it's a const iterator. So let's just put a comment here saying can't assign to const iterator. Okay. So those were the examples I wanted to show you that involve the set. So remember, sets have unique keys, unique elements in them. What we're going to do now is we're going to turn our attention to multisets. And as the name implies, and as I've mentioned many times before, a multiset is just like a regular set, except that you can have multiple keys with the same value. And we'll see some really cool examples of how to use that in a second. So you can have duplicate keys. Other than that, the signature is the same. So you take a type name key, you can have a compare functor, which defaults to less, just like set, and you can also override the allocator if you want to. So again, the characteristics of multiset, you can have objects of any types of keys, and they're sorted. You can have the keys are the only value that you've got. There's no value, there's just the key. And you can have multiple copies of the same key. Now, things that multisets are really good for, and sets are good too, but in a somewhat different way, you can use multisets with the STL set algorithms. And these include things like set union, set intersection, set difference, set symmetric difference, and so on. And one of the things that makes sets and multisets work so well with the set algorithms is that the set algorithms expect the values that they're manipulating to be sorted. Otherwise, they don't work. And so sets sort things, so they work very well with that. Of course, you could also use a vector and just sort it, but we're going to use sets here. We'll talk about using vectors with the set operations much later in the course. Okay, so remember some other interesting things. So when you have iterators to sets, if you end up removing or adding new elements into a set, then iterators to existing elements are not invalidated unless you happen to remove the item that you're trying to iterate over at the moment. But if you don't try to remove the item you're iterating over, the iterators actually kind of point into the nodes in the tree. So as long as those nodes don't go away, they can be rearranged, but the iterators to them will continue to work. And that's a little different for things like the vector and the deck, where they could be rearranged. I think vector is the biggest problematic one with respect to iterators potentially being invalidated when insertions occur, because under the hood, there could be a reallocation of the memory in the vector, and that would cause problems. So let's go ahead and take a look here. You can see that we're going to use the set container in conjunction with set algorithms, union, intersection, and set difference. And we're also going to demonstrate, of course, our typical trick of using copy to print the results out. So let's go ahead and see what we've got. So first of all, here's our first set A. And I just gave it a bunch of values. They're integers. And then set B has a bunch of other values that are also integers. These are not sorted, as you can see, but they will be sorted by the constructor of set, because it's going to put them into the red-black tree in the right order. And then we've got another set here, actually a multiset. These are all multisets that we're going to use to store some results in when we do symmetric difference calculations. So let's start out. We'll go ahead and print the copy of set A. It'll print it out in, of course, in sorted order. Then we're going to print the contents of set B, which will also be printed in sorted order. And then let's go ahead and figure out the union of set A and B. And so, of course, what set union is, as you may recall probably from your, I don't know, maybe your middle school or something like that, 7th grade or whatever, it's going to have the union of two sets will contain the elements that are in set A, in set B, or in both sets A and B. So it's the union of these things. And we're going to compute the union of set A by passing in the beginning and end of set A. We're going to go ahead and do the same thing for set B, and then we're going to put the results to the standard out using our O-stream adapter, our O-stream iterator. So we'll see what the results are in a second. Next thing we're going to do is we're going to go ahead and compute set intersection of sets A and B. And of course, as you may recall, again, from your set theory class at some point, that's going to be the elements that are in both A and B. So it'll be the intersection of the two sets. And then the final thing we're going to do is do a set difference between A and B. And that's going to end up creating a set that where the elements, it's going to contain the elements in set A that are not in set B. So it's like sort of like a subtraction, I guess, is the way to look at it. And then we print those out. And you'll notice for set difference, unlike set intersection and set union, you'll notice that we do an inserter instead of just writing the results directly to standard output using the O-stream iterator. And this is just to demonstrate what an inserter is. If you go ahead and take a look at inserter, you can see that inserter is one of these cool iterator adapters that we've talked about. And what you can do with these, and we'll talk about more of them later, these iterator adapters take a container, in this case a set, and turn it into an iterator, in this case an output iterator. And the way it works is it's going to make an instance of a struct or a class called insert iterator, and it's going to pass in the container and the iterator. And if we go over here and we peek down at insert iterator, we have to really poke around here a bit, you'll see that the way that this works under the hood is it goes ahead and will create an object that has various overloaded operations in there. And this will stash away the container and the iterator, and then there'll be various operations to move things around. In particular, you can see here the operator assignment, which you see at this point. And that's going to go ahead when it's called, and of course it'll be called as part of the copy algorithm, and the magic of the copy algorithm. It's going to go ahead and insert the value into the container using the iterator as a hint for that. So it's going to basically put it at the end, in other words. So that's what's going to happen. That's what's going to happen underneath the hood here. Okay, so let's scoot on back a little bit and run the program, and let's see what we get as output here. So you can see that the original sets, they're printed out, they're sorted, and we have all the values we had originally, except that now they're ordered in ascending order. We then compute set union, so that basically includes everybody who's in everything. We then do the intersection, and the only things that they have in common are 0, 1, 4, and 5. Set A does not have 2 in particular, so that doesn't show up in the intersection. And then the final computation, which is set C, is the set difference, and you can see that that's going to be the elements that are in set A that are not in set B. So you can see here that there are elements in set A that are not in set B, and those include these values that are shown there. For more information about the STL set algorithms, please take a look at the documentation. They go into great detail explaining the underlying concepts. And we'll also take a look later in the course at the implementations of these set algorithms. And they're really quite interesting. I think you'll get a kick out of that. Okay, so those are the things that I had wanted to cover today. I wanted to give you a feeling for how you can use STL sets, both regular sets that have no duplicates, as well as multisets that have duplicates, which we just used to show how the set algorithms worked. And what we'll do tomorrow is we're going to go ahead and do the same sort of a treatment, except we're going to be looking at STL maps. So we'll look at map and multi-map. And you'll see that those are some really cool data structures. And the examples we're going to look at for map and multi-map are really quite interesting. And they'll get a chance for us to show off the power of STL, how easy it is to write very sophisticated code with almost no work on your part, just knowing how to use the various elements that are part of the STL ordered associative containers. And we'll also start looking tomorrow at some other more advanced features in C++. These are features such as lambda functions, which are really interesting. If you're familiar with the way that Java has lambda expressions, C++ has a similar concept called a lambda function. And they're basically nameless pieces of code that you can declare sort of on the spot. And they're often very useful in C++ when you have functors and you don't want to go to the trouble of defining a specific class or a separate class to represent the behavior of the functor. They're most commonly used for defining things like operator function call and so on in a functor. So we'll take a look at that stuff tomorrow. Until then, thanks everybody for joining. Please go ahead and like and subscribe, and feel free to follow me on Twitter. Thanks.